Good. So, review of the previous lecture. Previous lecture, we talked about effective actions as the generating functional for 1PI diagrams. We argued for the the first derivative of the effective action, if you recall, by definition was a phi equal phi classical was J, right? Remember the analogy of classical finite temperature field theory? It's the thing, it's a functional whose saddle point or whose extrema give you the external source, right? The second derivative of it is, remember, inverse of the propagator, the 2-point, the 1PI 2-point function. And the nth derivative, we argued, well, we just structurally, I just structurally argue for the 3-point function, 4-point function, but you could push that discussion, and the natural consequence of it is that the endpoint derivative, and it's effective action, the generating functional for the endpoint 1PI diagrams. So before moving, so I decided to summarize the previous lecture by making a sharp point. The point I'll try to make, I'm not going to go over the discussions that we went over before. I'm just going to try to point out the following thing, that the fields and couplings in effective action are renormalized. Remember that it's a functional whose variation is going to give you phi class is going to give you the 1PI endpoint functions of the renormalized fields, right? So we're going to go over that today. So how does it work? Well, recall the way we're defining things. So here's phi renormalized. The 1-point function by definition is phi classical, right? If you remember, what we did before was that we wrote phi as phi renormalized times some constant, right? But that phi renormalized is taking a 1-point function like this. So I can always split my bare field as phi classical plus another bare field, which is a shifted bare field, right? So in this analysis, eta could be also will be renormalized. There will be a renormalized part. There will be counter terms in it. So the generating functional for connected, the generating functional for is e2 minus w of j. W of j is the generator for the connected correlators. It's the path integral over field phi e to the power of lambda phi plus j phi. Right? So what we're going to do is that we're going to plug in this expansion in the exponent. I'm going to pretend everything is like scalar field theory, but it won't matter for this argument. It's just you'll see. So here's the action. I'm plugging in the source action. I'm plugging in this expansion. So there will be the part of the action which is classical. The value of the action, right? Evaluated on phi classical plus j phi classical, right? Then to the next order, what I have to do is that I'll have to take derivatives of Lagrangian with respect to phi, right? And here's the first order eta that sits here. The coefficient of it is del lambda del phi x plus j of x. This vanishes. Equations of motion, right? Next order, we're going to have eta x, eta y. The second derivative, I think there's a sign here. How do I want to put it? I think, well, okay. I might, all these equations are correct up to minus signs. It's half integral over xy of eta x, eta y, the second derivative. I think there should be I probably want to put a minus here and a minus here. Right? And so on and so forth. So therefore, the partition function, right? Oh, by the way, sorry, I'm pretending everything is in statistical field theory, right? Just a Wick rotated thing. So I'm not putting I action over H bar. I'm writing e to the power of minus S Euclidean. Good. So it's Wick rotation. But I could put the I's and keep track of it. The argument will just go through formula. Because the only thing that it relies on is just extremization. So instead of finding the instead of, yeah, so. Good. So this piece is a constant integral over x of L phi classical plus J phi classical. Even if phi classical is a function that depends in space, this is a constant piece that comes out of the path integral because it's theta independent, right? So we redefine our path function now. Our the new field variable that we're path integrating over is eta, right? So now there will be the whole generating functional is going to be a constant piece, path integral over the field eta. The linear term dropped out, e to the power of minus integral half, second order, this guy. Do you have a sense of what this term looks like? What's the simplest, the first term part of this? So it's perhaps more canonical if I write it this way. What is this term? Does anyone have any guess? What does this term look like? Well, what is the action? What's the Lagrangian? The simplest term, the zeroth order thing is this, right? After an integration by parts is phi del squared phi, right? Varying with respect to two phi's is going to give you del squared. So plugging this back in, it just becomes a kinetic, standard kinetic term for eta. It's not, it looks fancy, but it's really nothing fancy, right? Now, this integral is Gaussian. We can do it exactly. And we did it exactly in the past, right? When we're quantizing, we're doing a path integral quantization of free fields, right? So the answer is going to be e to minus this constant bit that comes out, the determinant of this operator to the power of minus half. If you want to remember, recall how this was derived as this path integral, this Gaussian part of the path integral. Recall we had this identity. Just a bunch of Gaussian integrals, right? Times stuff that have to do with interactions. Good. So this bit captures which part of the, well, okay, maybe it's this. I'll explain that. All right. So this is the Gaussian bit, not the interactions. Take the log, so take the log of it. So this was e to minus w of j. Take the log of it to find, whoops. To find the generating functional for connected correlators, right? So it will be this term with a minus sign, but there's a minus sign here. Log of, there's a minus half, that minus, and yeah, that minus is fine. It gives you half log of determinant of this piece, right? Now, the clear observation is the generating functional plus other stuff, right? The generating functional for connected correlators depends on J, right? The source, but the only J dependence is in here. And if you recall, the definition of effective action is precisely W of J minus this term. So you end up with effective action being just the classical action evaluated on phi classical plus the second derivative term plus other corrections that are due to interactions. Now, allow me to put H bar in the game, back in the game. H bar, recall, is in a sense loop expansion, right? So coupling is also representing the same sort of expansion. If I want to put the H bar back in, effective action is similar to action. They both have 1 over H bar. This is the correction that is the next order, is order H bar to the power of 0. It integrates out all one loop diagrams. Order H bar is all one loop. The higher orders are, these are order H bar, and higher, these are higher loops. Right? So what I wrote for you is just a very formal analysis. As a very formal analysis, this is the expression for one loop expression, one loop answer for the effective action, written formally in terms of the effective Lagrangian. Any questions so far about this bit? This is in no way any different from the diagrammatics that we were working at in the previous two lectures. So it's equivalent to it, but I just wanted to give you another, instead of summarizing, going over it another time, I decided to do give you a different picture so they could compare. Any questions about this expression? All the one loop effects are captured in this log determinant. Of course, this is not, I just told you one contribution to it is del squared. That's the boring contribution. Well, actually, that's not so true. There's mass term, right? Okay, good. Now, from this, you could argue, after a few steps that I leave to you guys, that this guy is the generating functional for 1pi correlation. If you recall, the way we argued for that was we found, in the case of, for example, 3-point function, we found that the third derivative of effective action sitting next to 3 2-point propagators was giving you the 3-point function. The same was holding, that structure was continuing for an n-point function. You would always dress them with this like n 2-point functions, right, outside. The job of this guy is to generate those 2-point functions. I think it's just it's a good exercise to just keep taking derivatives of this guy. Let's see what you get. Any questions? Whoops, oh, sorry. So I jumped ahead. I was on this slide. Never mind. Good. Now, in none of this, I said anything about perturbative renormalized perturbation theory. So when I write this, when I said that you take derivatives and what comes out are going to be renormalized endpoint functions, I'll have to explain that. How does that work? So recall how renormalized perturbation theory worked. You take your bare Lagrangian, write it as the renormalized Lagrangian plus counterterms. Now, in our Lagrangian, bare Lagrangian, we also had the bare source and bare field coupled to each other. There will naturally be a splitting of the bare source into renormalized source plus some things that look like counterterms, because it's a rewrite. Now, the same way that del phi, this equation holds for the bare Lagrangian, this equation holds with the bare J, this equation will hold for the bare renormalized J. Now, all you need to do is to go over this expansion I had and split every term into phi renormalized, eta renormalized, or phi renormalized, and the counterterms, and follow it step by step. What you obtain is an expression that looks exactly like what I had before, but the only difference is that this is the bare action as before, but this is the renormalized Lagrangian derivatives with respect to renormalized field phi. I encourage you guys to do this before reading Peskin, cheating and reading Peskin, because Peskin does exactly that. Right? So what is the idea? Idea is you start with the effective action. Sorry, not effective. You start with a generating functional, you expand it as a 1-point function plus other bare fields, right? The shifted bare field. You write down, you integrate the path integral, you could to one loop, and you could write down the effect of one loop as a log of a determinant. That log of a determinant is like horribly divergent, right? Now, in this procedure, and then you see that if you were to construct the effective action, there was only one term that you had to cancel that was J dependent, and that's precisely the term that you drop, and you get some nice expression. If you repeat this analysis, splitting J into renormalized and not renormalized with the counter term and phi into renormalized and counter terms, this expression you end up with, and Peskin does that for you. Good. So you have some homework to do for yourself to make sense of this. Unfortunately, this section of Peskin is written in a weird way. Like it doesn't explain in advance why it's doing this and what is it doing. You might see a lot of like steps. So, any questions? All right. So this closes our discussion of effective actions. I'm not gonna discuss effective action for gauge fields for now. We might come back to it later. So if there are any questions about renormalized perturbation theory and effective actions, we're closing that chapter. Now is the time. So let me just say very high level. The principle of renormalized perturbation theory was that we define what a renormalizable theory is based on the dimension of coefficient couplings in the action, right? There was relevant and irrelevant and marginal operators. We define what a renormalized perturbation theory is, renormalized theory is, normalizable theory is. We said that for renormalizable theory, there is this prescription we defined as renormalized perturbation theory, splitting the field. For every field, we wrote field is equal to Z phi of R. That led to splitting of the action or Lagrangian into their plus counter terms. We treated the counter terms as interactions for the renormalized fields. We did Feynman diagrams. We saw that we could tune the coefficients of the counter terms to cancel the divergences order by order in perturbation theory. We argued that we saw some examples of this at two loop, and we said there's a theorem that guarantees you could do this in arbitrary loop. We also discussed in the presence of one-point functions, when you have spontaneous symmetry breaking, you are in this weird situation that at first it seems kind of magical that you have less, the number of counter terms that you have compared to all these interactions that you have might seem confusing. It's kind of, it seems magical that these counter terms can cancel all the divergences. But we saw examples of that. And we said that in the cases that you have spontaneous symmetry breaking, mean that the field phi can acquire one-point functions. You define phi classical, you shift the field, we define effective action whose variation gives you the one pi endpoint. So that's the summary of this whole section. That's all you need to know. We made an analogy with StatMech, so hopefully that part is clear. Every time you find yourself, yeah.
This is when we discuss symmetry breaking.
Yeah.
We discussed the linear sigma model.
Yeah.
And we saw that the classically Wilson said that we have massless modes.
Yeah.
And we saw that quantum mechanical also they remain massless.
Right.
Does this statement remain true for any symmetry breaking, so to say? Or are there
gold sum? Sorry, it has to be continuous symmetries. So the gold sum theorem says for every continuous degree of symmetry, degree of freedom that you spontaneously break, there exists a massless scalar that we call Namu-Gold sum of. So there's a theorem. Doesn't matter what your action is, or quantum mechanically remain also massless.
So does that always hold? Like
the fact that quantum corrections cannot give mass, yes. Yeah.
For any like continuous symmetry you break.
Correct. It's very powerful. Just a little thing. A lot of times when we are giving these examples of like funky non-perturbative or like fancy examples of quantum field theory effects, the way to give an example, to work out an example, is to go to sit in lower dimensions, 1 + 1D. Often you can actually make analytic progress. In this spontaneous symmetry breaking case, you shouldn't do that because you cannot have spontaneous symmetry breaking 1 + 1. That's an important result, and there's beautiful physics associated with it. All right. Any other questions before we close this chapter? If it's all good, let's start renormalization groups. I think they've been promising for a while. So let's start renormalization group first by collecting all the physics we observed by doing normalized perturbation theory. And then I'll zoom out, take these lessons, connect with the principle of separation of scales that I kept talking about from part 1 of the course, KFT1. Try to make sense of it, and we're gonna systematically build on top of this, okay? A lot of what I say is, well, today's what I say is called Wilsonian renormalization group. It was first discovered by Wilson in the context of in terms of statistical field theory, right? Fine temperature quantum field, classical fields. But the same sort of logic also applies in after weak rotation and relative to quantum field. All right. So this is called Wilsonian RG. There's also something called exact RG. So we might comment on those things. I think I'm gonna start to do that. All right. So recall perturbation theory. Feynman diagrams, all of that. In perturbation theory, we saw that every time we're looking at quantum corrections. Quantum corrections show themselves in terms of loops, right? Higher and higher order loops meant higher and higher orders in H bar. So they represent quantum corrections or quantum fluctuations. In Feynman diagrams, every time we had a loop, we had an integral over a momentum running in the loop, and the momentum could be anything, right? The value of the momentum could go from 0 to infinity in the normal event. This means the physics of that is that quantum fluctuations exist at all energy scales. So quantum fields are fluctuating at all energy scales. If this was statistical physics, it would mean that thermal fluctuations exist at all energy scales. Just very, very high energy fluctuations are extremely rare. However, by Boltzmann weight, they exist. But because of Boltzmann weight, they are rare, but they exist, right? Now, large p squared in loops is what gave us a hard time, divergences. These are high energy fluctuations. These have to do with short distance physics, right? The whole point of renormalized perturbation theory was to establish that you could cancel the divergences by appropriate counterterms, by adjusting the couplings, by shifting in the couplings. This means that high energy quantum fluctuations do not alter the long distance physics. Right? The fact that it could cancel them meant that the only thing they could do is just shift a few couplings and renormalize them, shift the value of them. There was no other way they could contribute to anything else, right? This is the principle of separation of scales. It's telling you that long distance, low energy modes depend on short distance modes on a very, very weak sense that the effect of the high energy modes is just change the couplings of the low energy modes, how strongly they couple. It's just a bunch of coefficients. They can't have a more sophisticated effect. And this is the principle of separation of scales. It's a deep, deep principle. The fact that nature nature around us is renormalizable is why we can build buildings, we could do engineering. Ethical MA holds, right? Ethical MA is some effective theory constructed for low energy excitations. We don't have string theory, all of that yet, but somehow as a phenomena, this ethical MA has all sorts of quantum corrections. Quantum corrections are coming from all insanely high energy physics that we haven't discovered yet. The fact that ethical MA works is a statement that it really doesn't matter what the UV physics is. The only thing it could change is just the value of M. Coefficients, right? Couplings. We could build predictable theories because we're lucky to have low energy physics that's renormalizable. All right. And it's just again the set of words is separation of scales, like UV physics and IR physics. These guys, they average out. In a sense, these fluctuations average out up to just some coefficient shifts of couplings up here, right? Said differently, if you look at the renormalized endpoint function of renormalized field, this thing is independent of the cutoff. So in a sense, if the UV physics doesn't matter, the integrals don't matter, why just integrate over them? You could just cut them off, right? So we had our bare fields, we split them into renormalized plus counter terms. The counter terms were interactions, right? The infinities were canceling out between bare fields and these, the counter terms, right? So you could choose to, so the UV modes run in both of them, right? They both have UV modes and they cancel exactly. So if they cancel exactly, you want to go just not integrate over the bare fields above a certain energy scale, not integrate over the counter terms above a certain energy scale, right? It won't matter for the physics. As long as you, at the end of the day, you go and tune your renormalized values by measurements, it won't matter. So it's in that sense independent of the cutoff, right? It's not just a cutoff. Like I could just arbitrarily suppress the UV modes as I wish, or modify them as I wish, and it won't matter. The amount of them, right? And this is actually, this sharp cutoff is one way of thinking about it. That's Wilsonian RG. The smoothly suppressing the UV modes is what's called exact RG. We're going to see that. There's actually a conceptual advantage for the update. Is the principle clear? All right, so Wilsonian RG is this brilliant way of, as such a simple argument, but it's deep, and it really revolutionized the way we understand quantum field theory. The argument is super simple. I'm just going to run it very quickly. Imagine, so what I'm trying to argue is that how is it possible that the effect of the UV modes could be captured as just a bunch of shifts in the coupling? So we're going to try to see how that's possible and how true that is. Not every theory we construct is renormalizable. I also said at the very beginning that, oh, renormalizability is not a big deal. We make a big deal out of it in this course at the beginning, but not that much of a big deal. So we're going to discuss all of that. All right, so here's the super simple argument of Wilson and Leo Kadanoff. Take your generating functional. It's an integral of path integral over phi, e to the power of I s action plus coupled to a source. And as far as I'm concerned, I could put a minus sign here. These are Euclidean actions, becomes statistical field theory, right? So what is this path integral? Well, you know that from perturbation theory, we usually can Fourier transform this and write this as an integral, as a multiple integrals over 5k modes. So each momentum mode, there corresponds a field, and you're integrating over each of those guys. And there's an infinite number of these guys. So a sharp momentum cutoff means that, well, this is like an uncountably infinite set of variables. Let's just cut them off at some large k. This is absolute value of k, right? So k squared, k mu, k mu. So you do the Wick rotation, all that song and dance, right? Sharp momentum cutoff means, another way of saying it is that, well, you could keep the integral, but here in your fields, just put phi of k equals 0 for all k larger than lambda. It's the same thing. For the sake of concreteness, I'm going to pick sign minus here and talk about statistical field theory because it's a little bit cleaner. I don't want to keep i's around. I'm going to use this notation. This d phi lambda means only integrate, path integrate over modes lighter than some cutoff. So this is like a hard regulator that we use, right? We said that it's not always kosher, it violates, it's offensive when you have gauge theory, blah, 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 but let's just do it for now, for the sake of argument. All right, so what are we going to do? To show that our calculations are independent of the cutoff, one simple way is just to change the cutoff, right? But you can't change the cutoff. The cutoff is integrated as a set of integrals. So let's take this is range of integrals. So we're integrating over this range from k to 0 to lambda. Let's explicitly perform the integral on a thin momentum shell from lambda to b lambda, a little bit smaller. That corresponds to shifting the cutoff, right? I'm just going to take my integrals, right? Take my path integral with cutoffs less than lambda, separate the part of the integral that has to do with modes between lambda and b lambda, give that a name phi hat. Hat doesn't mean operator, right? Just give it a hat name, phi hat. And write this set of integrals as a bunch of less integrals multiplied by this particular integral. Let's say b is very, very near 1. So it's just I'm identifying 1 bit. Okay. So to show that the correlation functions are independent of omega of lambda, I should be able to perform this bit of calculations and reabsorb the result of that shift in the cutoff as a bunch of shifts in the couplings. The only thing that can change is shifts in the couplings, right? All right, so let's do that. The old field was running from k less than 0 to lambda, and now this guy is the new field plus this range. Okay. Our old path integral can be written as a new path integral times this new path integral over the field phi in this range, phi hat, right? And now I just plug in this splitting, right, inside these expression in my Lagrange. And now you see why I went through the background field methods before doing RG, because that was all about shifting the field and plugging in the action. All right. So what we want to do is the following. We first notice that I can expand this. I'm going to get a whole bunch of terms that are phi and a bunch of terms that are dependent on phi hat. The terms that are dependent on phi, I'm just going to pull them out of the integral of d phi hat. So there will be this term, right? Out of this expansion always comes that L of phi, right? So this is this part. This looks like the action with a new cutoff, lower cutoff, the same action with the lower cutoff. Now the remainder is going to be path integral over this momentum shell of all the interaction terms. So there will be a bit that is minus half phi hat squared plus the mass of that mode, right? It's a massive mode, plus interaction. So the light modes and the thin shell mode, there's phi 4, 3 of them could be this, 1 this, 2, 2, 1, 3, 4, right? It's just an expansion. Now, this path integral, as a path integral over phi hat, I could do explicitly. I could evaluate explicitly, and the result is going to be a function of phi, right? That I can take a log of and interpret, put in the action as a change in the Lagrangian of phi. Let's stare at this until it sinks in, right? So it's a little bit like this. I had 3 integrals, right? It's a little bit like I had integral over x, I had integral over y, integral over z, and some function f of x and y and z. I did this part of the integral, right, to get a function of x and y, right, and stare at this. I just viewed it this way. So this was actually originally some f of x, or whatever, you know what. So I'm just doing part of the integral. It's a thin momentum shell, path integral, right? But this L effective hopefully is clearly different from the L original, because there are these terms that will contribute as, but I'll have to take a log of it, right? Because this is what comes out of this is just a polynomial, right? But this polynomial to low order perturbation theory, I could also regenerate it using these exponents, right? Yeah.
How do you go from here to arguing that the effect of this function of phi is just a shift in the
Oh, I haven't done that yet. Those are the next slides. But formally is true in the following sense. So look, this answer is a functional of phi. If the functional comes out to be a local functional of phi, right? Say at one loop, let's just focus on one loop. If it comes out to be a local functional of phi, at one loop, I can view it as just an exponent term. Right? By the way, what order this starts at one loop. Do you guys know why? Why is this functional starting at one? So let's look at the first part of it. One loop means order, like there's lambda dependence. Right? Sorry, I shouldn't say one loop. Source of order lambda, right? This is not lambda dependent. So if you pass it over this part, it's just a number. It's a number. So it's not it's not like a functional at all. It's just a number. So we could view it as normalization. This part, right, is the part that's going to contribute to the functional, and it's order lambda. Because it came from interactions. Right? So it's going to sit here and it's going to start at order lambda. Good. So L effective is gonna look like old L plus order lambda L effective part one. Like I shouldn't call this one loop. I think that's misleading. That's incorrect. And then order lambda squared and blah blah blah. Good. As the principle clear, it's essential that this step is very, very clear. Because the rest of whatever I conclude is going to follow from this, and there's a lot to conclude. Yeah.
Yeah, just one clarification. Here, L effective is having the dependence on lambda, right? We can clearly see.
Yeah, for sure.
Yeah, but when we are integrating out here, the argument was that it, like our Z lambda shouldn't depend on the cutoff, right?
So capital lambda. The cutoff is capital lambda.
Yeah,
This is little lambda.
yeah.
Sorry, I'm using abusing notation. Capital lambda is the cutoff. So in this notation, it should not depend on B. Right? Because I'm shifting Z to BZ. All right. So let's try to do this. Oh, actually, pause again. Is this clear? Is this absolutely clear? This argument is perhaps one of the most important arguments in quantum field theory. Okay, so let's do this path, at least schematically. So what does it look like? It looks like integral over d of phi hat, the kinetic part times lambda interaction part. And this interaction part has phi dependence in it that we're after. The result of this is going to be a functional of phi, low energy mode. So phi hat is UV mode, phi is low energy. All right. So let's expand this as 1 plus lambda v of phi, blah, blah, blah. So how do we do this perturbation? Let's just try to do perturbation theory in small lambda, right? Good old perturbation theory. The first thing you would do is you would find the propagator for this phi hat field. The propagator for it is obvious. It's 1 over k squared plus m squared. This bit is just normalization. And then there is the, whatever this is called, the theta function, no, it's not. Characteristic function, right? Like this is supported.
Yeah,
Yeah, so as a function of lambda, it's supported only between lambda as a function of, a k, I'll call it p, k, as a function of k, right? It's only supported between lambda and that, and it's zero elsewhere, right? Because that's the range of momentum. Yeah, I had the definition down here. I didn't. All right, so it's clear. That's the 2-point function, and you have to do final perturbation. You could do that, but let me tell you. Actually, let me tell you in advance what's going to happen because we have limited time in class, and I just want to give you the structure of it. So if I were just not doing the path integral over phi hat, and I was just organizing this the way that we did in normalized perturbation theory, right? Writing that saying phi hat is a different field than phi. The propagator for phi is this line. Propagator for phi hat is this double line. What and then phi field has this vertex interaction, 4-point interaction. What kind of interactions am I going to get? So let's stare at this. I'm going to get a phi cube phi term, phi 2 phi hat 2. So phi cube phi hat cube, and so on and so forth, right? So these are the 4 diagrams I'm going to get. Remember that the conservation of momentum is key here, right? So this guy has larger momentum than these guys, but the 3 of them could add up to this, right? And similarly here, right? Okay. Hopefully there are no hesitations, but some of these, I'm not going to argue with that. All right, so let's see first, how could the effect of this phi hat be a renormalization of mass, right? So let's look at the 2-point function field phi. Well, there's a contribution to this guy from phi hat that we're going to integrate over, right? So there's this diagram. This is a correction to the propagator of phi at one loop. What does this propagate? What does this look like? This looks like the 2-point function of phi hat, phi squared, integral of d4 minus lambda over 4. It comes from this term. It comes from this term, right? Because if I integrate only this term, first of all, it's order lambda. It involves a propagator of phi hat because it's just second order, and the rest is just a coefficient, right? So the contribution of that term is gonna look like integral of half integral over k, right? Phi k, phi minus k. I'm just going to the momentum space, right? And a mu is a contribution of this loop. So what is that? This loop is just 1 over k squared. This is actually not quite k squared. This is 1 over k squared plus m squared. But I'm assuming that lambda, the cutoff, is much larger than m squared, so I can drop that term. I'm going to come back to this. Okay, this is important. But it's a simplification I do for now. All right. So this should be actually 1 over k squared plus m squared, but because there's in the propagator, the k is between lambda and b lambda, and this is much larger than beta, I'm just going to drop that term. What are the corrections to this approximation? They're going to have extra powers of k in them, right? Upstairs. All right, so let's forget about those corrections. What is it going to look like? We did this integral. Well, this integral we could do explicitly is b2 by, this is the expression. This is literally expression. All right. Okay, so it is what it is. This is just the value of it. But what does this do? It shifts the 2-point function. It shifts the mass. So this is contributing to the normalization of the mass of the light fields. Imagine I'm an observer who has detectors that are arbitrarily precise, but they can measure only up to a certain energy scale. Right? Now, this physics is invisible to me. I cannot understand that. I cannot distinguish between this and this. So I have to add them up. That's what the physics is, right? If you cannot distinguish between the 2 diagrams, you have to add. All right. So first lesson, we just see that the functional, this path integral will give you corrections to, for example, master. So let's see what kind of other corrections we had. Can we get a correction to a vertex? 4-point function. Yes, we can, right? This is a correction to a 4-point function. We had this term. This is a phi cube phi term, right? This is a, yeah, you know where I'm going. But in this perturbation theory, you can never have a phi hat as an external leg, right? That's not what you're after. All right, so what does this, let's just focus on this term. What does this look like? this looks like, well, it's an integral with two propagators of this heavy field that I'm this approximation. I'm going to write over as 1 over k squared over 2. The integral runs over this window, this narrow window, right? So this is k is between lambda and b lambda, right? And this the rest is coming from there are two vertices, so it's lambda squared is one loop. I've been saying incorrectly, right? You know what I mean. One loop is lambda squared here, and these are the rest is just commutatorics. Good. All right, you could do the integral explicitly. You get lambda squared 1 minus b to the power of d minus 4 over d4 lambda to the power of d minus 4. Now, I'm already treating d as if it's just an arbitrary dimension. In 4 dimensions, this becomes 0, this becomes 0. You take the limit properly, and you get log of 1 over b. So there's a log correction. This is going to be crucial. It is a correction. This is a correction to the vertex by its log. These logs are the same logs that we saw we had to cancel in a normalized perturbation theory. We had to make sure that they cancel out. Good. So far so good. Is this point clear? It's a good point to pause because the next I'm going to tell you about. So far it's not wacky. The next step is something funny. Under this path integral, there are brand new interactions that pop up. This is a legitimate diagram that an observer with low energy observer will see as a contribution to a 6-point function. But the low energy theory didn't have a 6-point function. So what does it mean? It means that it was probably not 0. It means that if the observer assumed that there was no 6-point function, they were assuming some sort of magical cancellation of terms. It has to be there naturally. Under the normalization group is generated. So if I'm a low energy observer and I start writing an effective action, an action for my low energy modes, not knowing about the U deep in the UV, string theory, all that crap, right? I'm just going to go up to a certain order, right? And I'm just going to pronounce this theory is all that there is, right? The contribution of higher energy modes are just going to be only captured in these couplings and no more. That requires some fine tuning, some magic. It's not going to naturally happen. So naturally, crazy terms are going to be generated. So let's see how this term is generated. Oops, what am I doing? All right. So this term is proportional to lambda squared. Oops. Okay, I'm not touching this. All right. P1 plus P2 plus P3 squared is just the momentum conversion momentum propagating here. And this is that characteristic constant, right? It's probably over there. Lambda 6 was 0, but it was corrected. So quantum mechanically, you shouldn't expect low energy theories to just have a bunch of terms. Now, what happened to that whole argument that we had a long time ago, right? We said, oh, only the nice theories are only those that have like a few terms and they're normalizable. Because we said that if you go to higher and higher order terms, they're just going to be like worse and worse. They're going to be more and more irrelevant and they're terrible. So from this point of view, if you don't know about the UV, everything goes. So if you're building an effective field theory, you should not worry about renormalization. So we're going to come back to this. So what does renormalization mean? Or does renormalizability mean? Actually, so this 6-point, is this point clear? The 6-point function will appear naturally. Now, so it looks like you should always include in low energy action some expansion in phi, right? Because you don't know what's going on in the UV. But it's actually a little bit worse than that. I treated these propagators because I said, oh, the cutoff is very high energy, so the propagator of this mode is like 1 over k squared, but it's not quite 1 over k squared. It's 1 over k squared minus m squared. So when you expand that and m squared over lambda, so that's what the expansion parameter is, right? If you expand on this, you're going to find that there will be extra powers of k in your interactions. In real space, that means terms like this. Every power order of k is like a derivative. In your effective action, well, in your action to start with, there was no principle that told you. You remember when we saw that local action, we said it has to be a function of phi and del phi. We started by writing del phi squared for clear reasons, but we didn't write del phi cubed, del phi 4, blah, blah, blah. We could have, right? And we see they're actually generated. So we should have. Of course, they're going to always come in a way that preserves relativity, right? Is this point very clear? I want to make this very clear. So interactions are going to get generated in the infrared, always. All sorts of crazy interactions are going to get generated. You have no control over it.
I'm a bit confused.
Yeah.
So you're saying that interaction, so when you go from UV to IR, interaction are like this lambda 6 and things become non-zero. And you go in this direction.
So they're going to get generated. Now next step, I'm going to explain what's going on. But I'm just saying that tuning them to be zero requires fine tuning. Quantum correction will make them non-zero. Is that clear? Ask your question.
And maybe later. Maybe
Okay, make sure we come back. Okay. So now it seems like we're in a terrible position, right? It seems like anything goes, and it's just horribly out of control. But luckily, like renormalization group is actually a systematic way of studying this problem, and it actually tells you exactly what is going on. So the relevant and irrelevant and marginal operators and their relevance, their importance is going to be our next one. But let's pause again here for questions. Fundamentally, from the point of view of a low energy observer, anything that preserves Lorentz invariance goes. Now, of course, hard derivative terms are more suppressed. Why? In the infrared. There are hard powers of k, right? K is dimension full. What is the parameter that's small? K over lambda, right? So these corrections are, of course, one or like m squared over lambda squared, k squared over lambda squared suppressed, for sure, right? So already you can see from the point of view of the low energy observer, if they don't care about insane precision, they could just treat these terms as zero, right? But if they want to be very, very precise, they have to take them into account. To treat, now the issue comes up with treating in renormalized perturbation theory, we want our Feynman diagrams to not represent an approximate answer. We want this to be the full story all the way to the UV, right? That requires a lot. They're asking a lot from the theory, right? And that is why we're ending up in this land of very special theories. But we're going to discuss that actually in a bit. Good. So now I'm telling you that actually from the point of low energy of physics, not only should include higher powers of phi, should also include the derivative. So the Lagrangian is going to look like this in power series, Taylor expanded, and phi and del phi. Do think about how such terms pop up. All right. What I just described to you is not RG flow yet. This was step one. There are two steps to RG flow. Step one, Wilsonian RG flow. Integrate out a tiny momentum shell. Step two, rescale the fields, space and fields, such that you bring the cutoff back to what it was. So we're going to see that in a second. So just keep that in mind. We're going to do that. So far what we did was that we did it this way. We said the path integral for k less than lambda is equal to path integral for fields with a lower cutoff, but a different action. That's correct. That's so far what we've said. You could call this the end of the story and say that this is renormalization group. That's legitimate. That's all good and fine. But the next step makes some other stuff clear, we're gonna use to write down equations for flow of couplings, right? So that's what we're doing. Well, actually, you will already see why I'm doing this. So what we wanted to say is, what we showed so far is that you change the cutoff and the couplings change, right? Now, what we want to say is, this is not what we did in renormalized perturbation theory. We said we have a very, very high energy cutoff, right? We had a renormalization scale that whatever the integral of these like modes, the contribution of these modes from the cutoff to this was, the scale of interest was. We don't care about it. We're just gonna call the sum of that. It was sum up to the normalized answer that you observed. You put in by hand, right? Now, as you change, now that answer, just like the relation to some imaginary cutoff is in your mind, right? That's the connection between renormalized field and bare fields, right? It's all in our head. It's imaginary and made up. The physical thing is that now what happens if you keep the cutoff fixed, but change the value of your renormalization scale? If you normalize your field at different scales. That is what we're after. So we're after the dependence of the couplings on the renormalization scale, not on the cutoff. That's why in the next step, we rescale things back so that the cutoff is back to what it was. Now the only thing that's changed is just your renormalization scale. Right? Is the logic clear? But in principle, you could make sense of RG in the first as one step thing. Right? You'll see both of the pictures depending on which paper you read. But hopefully I articulated the story well. All right. So what do we have so far? What we have so far is that this L effective looks like the good old L, right? 1 m squared phi squared, lambda phi 4, and other stuff, right? But there are these corrections. Delta Z, due to a tiny integral that we did, this is a correction of the kinetic term, right? This is a field renormalization. There is a shift in the mass, shift in the coupling, shift in the couplings you thought were 0. Right? So they're all of these. Okay, so how to bring the cutoff back? To bring the cutoff back, we have to rescale by defining some new k. K prime is k over b, right? Then this comes back where it was. But if you do that, this is understood as a space-time transformation, right? You're just changing your meters, your units. So this means that your x is changing. X prime is xp. Now that changes this integral. Is that point clear? So you could bring this guy back to this form at the cost of changing the x, this effective action. All right, so let's see how it works. But before doing, okay, actually, yeah, let me not go over this while you see it. That's an advanced comment. So let's just skip that for now. So what does happen? What happens? Well, I can write down this d4 of x as d4 dd of x prime b2 power of minus d, right? Because of this relation. There is derivative. Every time I have derivatives, these derivatives become derivative prime and b's appear, right? And that's the only change. Question?
Yeah, and I earlier we were not wanting the dependence on B, right? But now we can clearly see the dependence on B.
Oh, because I mean, I said I brought the cutoff from lambda to b lambda. I want to pretend that capital lambda is fixed.
Okay.
B is the only thing that I'm changing, right? Good.
Yeah.
So if you wish, B is lambda over lambda prime. All right. Lambda prime over lambda. Okay, now we observe something funny. Well, it's not funny. You could have guessed it before. If you redefine your fields this way, right, from the kinetic term, so you define a phi prime, this could be eaten in here, and at least this kinetic term comes back to what it looks like, what it looked like. But now all the other terms are going to change. But they're going to look like this. They're all going to look like new couplings. A space-time transformation, when you scale fixed fields by x to send x to x prime, the way they did it, right? And the field transforms this way, is called a conformal transformation, wild transformation, dilatation. The proper way of doing it is to call it a wild transformation and view it as not changing x, but changing the metric. You're just making your rulers different. You're picking a different set of rulers. This is called a wild transformation. It's a symmetry of classical conformal actions, conformal, right? Yeah. Which term is conformal here? Just the very first term. That's why in renormalized perturbation theory, all we needed to do was just to define field phi is z phi r. The rest just pops out, right? Like the rest comes out. The only thing we want to keep canonical is the kinetic term. Mass is treated as an interaction, right? Mass actually grows as under a renormalization group grows towards the infrared. Now this is a fair comparison. Now you could actually compare this guy. I'm making a mess here. I used to be better at this. Now I can make a fair comparison between this action and the action before integrating things out. Now my couplings depend on what? B. How? In the following way. M prime of 2 is of this form, and this form. And these guys I have to calculate by doing those loop intervals, right? Depending on my theory. This is called renormalization group flow couplings. The couplings change as you go to low energy. Good? Now, when I said that the couplings change, right? All I was saying is that there's no reason for delta Z, delta lambda, delta C, and delta D to be non-zero, to be zero. They're generically non-zero. So if you pick C and D as the initial values to be zero, it's silly because these guys become non-zero. However, the catch is if B is to some positive power, remember B is less than 1. If this is to some positive power, deep in the infrared, even though this is non-zero, but it's suppressed. This is the same argument that I said, oh, there could be all sorts of higher derivative of crazy terms, but in the infrared, I just don't see them. I'm not sensitive enough. So to make sense of that, what do we say? We make the following, so let me go over it again. If it's a thin momentum shell, another thing. If it's a thin momentum shell, these transformations become like continuous. So they're like differential equations. The fields depend on, the couplings depend on B. And you're talking about the derivatives of the couplings as a function of B, as a function of scale. Question? Okay. Any other questions? And the grand renormalization picture is the endpoint functions of the field phi with lambda and L, some initial action, is equal to phi primes of P primes of lambda, same lambda, L effective. This is fully non-perturbative, right? It doesn't matter what I integrate or what. Like it's thin shell or not, whatever, I don't care. This is the grand thing. This is the thing that we're going to massage into what comes out as the Callan-Simanzik equation, the differential equation for the flow of the couplings. So as I said, the simplest case possible is just a kinetic term. That's where all the couplings are zero. This is a fixed point of renormalization group flow. If you do the 2 steps that I just described to you, you get back your initial action. nothing ever runs. If you set these guys to 0, if this is your action, it doesn't change under. Good. Now the relevance of the second step becomes clear. If I didn't rescale back, right, things would change. So it's harder to make sense of a fixed point. Yeah.
Shortening that, but are all fixed points of RG's conformal field series?
Yes. Sorry, no, my bad. RG is a scaling transformation. By definition, the fixed points of RG are scale invariant theories. If you're talking about relativistic theories, where relativity is preserved along RG, as all these examples that we'll be talking about, it becomes a question of, can you have a scale invariant relativistic theory that's not conformal? That's what you're asking. That's what I was discussing.
Yeah.
Now, you break relativity, scale invariance and conformal are very different things. Good. Now, near L0, you could ignore these guys because these are lambda corrections. And what you find is you could solve these equations, and like you look at this, you could ignore these corrections. And what you find is basically m prime 2 is m2, b2 minus 2, lambda prime is da da da, and that's all you find, right? This is nothing but that naive dimension counting thing we were doing at the beginning of renormalization before. It seemed like so random at the beginning, but we're just recovering that. And this is the analysis. If you recall, that was the basis of analysis, that was that if this power is positive, it decays in the IR, right? If it's negative, it grows in the IR. We call this relevant, irrelevant, marginal. So from the point of view of an infrared observer, you can't, it's simple, it's just insane to assume an irrelevant, a relevant operator is not present, right? Because that requires magic, sheer magic. Because not only, if it's a teeny tiny, there was a teeny tiny contribution somewhere in the theory, it would just grow. However, the other way around, if it's an irrelevant, you say, oh, I don't care. Even if it were something, it would just decay. So as an effective field theorist, as someone who works with finite precision, I just don't care about it. Right? Marginal is just means it doesn't change along the flow, so you gotta take it seriously. How could it be? Can you come up with a principle, just naively, for a low energy observer who writes an action but doesn't write a relevant term? What from the principles of quantum field theory I've been telling you guys, what allows you to do such a thing? Symmetry. The only way you could rule out irrelevant deformation is symmetry. That's why the principles of quantum field theory, we start saying locality, symmetry, separation of scales. By that, I meant this analysis. Anything that's relevant should be there. Now imagine, so if you're only focused, now you're a low energy observer, you're writing only relevant terms. That's actually, those are the renormalizable theories. Those are the theories that are nice, and we call them renormalizable, and solve it. Now, let's say I'm an observer and I see something that's non-renormalizable, like general relativity. I see an action in my theory, it's non-renormalizable. How am I going to interpret that? It's an irrelevant term, but it's not small. What does that mean? How could an irrelevant term not be small? Think about that. That's a very, very important question. I've already given you the answer a couple of lectures back, just colloquially, but let's think about that. There are theories. General relativity is an example. It's an important theory in nature. It's not renormalizable, and it's an IR theory. It's an infrared theory, and it's the irrelevant terms that are large. What's the interpretation of that? All right. It's my last slide for today. So let me say this. As I said, along the renormalization group flow, all operators with arbitrary numbers of 5 and derivatives will appear. So think of it as a collection of 5, 5, 5, 5. It's like how it works. A bunch of del, put them in different places, mu's, all of them. They will all be there, right? You can do a simple naive dimension counting. You can count n powers of phi and n powers of derivatives and call that operator CNM, right? That operator, the naive dimension counting of it is like this. So it scales this way on the RG flow. B to the power of n, d minus 2 minus 1, plus m minus d. Can you guys argue why this is? Well, you go through it. This is just naive dimension counting. There's nothing fancy. So an operator that's order OI, an operator OI with mass dimension di has a coupling of dimension di minus d, and then of course, because the coupling will end up being dimension full, the only sensible perturbation theory would be in terms of dimension-less couplings. So if you have a dimension full coupling, what's actually sitting next to it is P over lambda to the power of di minus d, right? Now, if this is a positive value where di is larger than d, in renormalization group, we keep the cutoff fixed. We pick smaller p. That means in the infrared becomes irrelevant, unimportant and low p, and the other case would be relevant. Could di be negative? No, we could convince ourselves that's true. So this is a positive number, and it's for it to be relevant, it has to be bounded by this dimensionality has to be the energy mass dimension should be bounded by d. This tells you that the number of relevant operators, the number of possible relevant terms you could write down in your Lagrangian is very limited. That is why the nature is so nice. There are very few in the world of in the UV, there are millions of direct terms that you could allow, infinite number of terms you could allow in your Lagrangian. The vast majority of them don't matter. For the same reason that lecture 1 of QFT1, we talked about the spin model with all sorts of microscopic details. But who cares? All you see in the infrared is phonons. They're all averaged out, right? I don't see the distinction between all, like if I see some magnetization over a chunk of metal, I can't resolve the microstatics. It doesn't matter, right? So the relevant modes are, and those operators that flip one side, like microscopically, that's a UV mode, and it's irrelevant. It can't possibly affect my physics. All right. I did not write the summary, but let me just summarize in words. Today, let's forget about the effective action story for the sake of time. We started a renormalization group flow, systematic study of it, okay? And to connect with the previous discussion, we started with Wilsonian renormalization group, which was based on a sharp cutoff and integrating out a thin momentum shell to bring the cutoff down. That was step 1. And then performance scaling to bring the cutoff back up, right? But then the effective action, the action, effective Lagrangian will change. And the coupling will change, and that's what we called renormalization group flow. Well, we went over a lot of things, but I want to just clarify the following point that I said it many times, that from the point of renormalization group, anything that's allowed by symmetries goes. The next principle, anything that local is allowed by symmetries goes. Actually, think about this. Could non-locality develop the renormalization group flow? Does renormalization group flow preserve locality? That's an important question. The answer is very obvious, but once you think about it correctly, it's obvious. But right? But also there's a principle which is separation of scales, which means that in your action, if you are a low energy observer, finer precision, you do a derivative expansion, an expansion field. And that's that's going to be based on relevant operators, and that's like captured in physics. So put that aside. I'm not going to summarize anymore. We're going to go through this. We're going to discuss this in more detail in the next couple of lectures. But I want to say one thing. Back in the 30s, Landau was trying to make sense of phase transitions. And he realized he wanted to write that this is fine temperature classical field theory, right? He wanted to write down, he didn't know anything about what was going on, right? He wanted to make sense of theories that describe, like phase transitions and like they undergo like the spontaneous symmetry breaking and all that. He wanted to write down an action just from out of nowhere, right? Whose variation, he was willing to do a bunch of measurements to tune a bunch of coefficients. The action had to have a bunch of coefficients. He would do a bunch of measurements to tune those coefficients and then use this action to predict things. This was his task. And he wanted this action to describe all sorts of like critical phenomena, like spontaneous symmetry breaking and such, right? Order. And his principles were precisely this: locality, symmetry, expansion in derivative and field. This is a long, long time ago, but he got the three of them on the notes. Landau was a big guy. He contributed so profoundly to physics. After so much development, we understand the underlying principles of it, but he was on the right track, right? So renormalization group story goes all the way back to the study of early 20th century. All right, any questions? If not, let me just say one